So I think we are ready for the webinar. This is last check. So Radek, can you hear us? Can you see us?
Yes, I think so. I can see you, I can hear you. So the last check is done.
Okay, fair enough. So I guess we can start. It's 2 p.m. and I'm sure the best part is still to come. So I think we can start the webinar. So yeah, let's start it. So hello everyone. This is Luboš Pirkl from CFD Support. And I would like to welcome you to the webinar where we will talk about simulations of centrifugal pumps. Specifically, we will talk about CFD and related FEA and FSI, and yeah, it can end up with the optimization. So yeah, so this is the webinar. So we will be happy to show it to you. The webinar is being recorded, so the recording will be later publicly available. So you can take you can see it in your leisure time. What else? There will be like 3 parts in the webinar. In the first general part, I will make a quick introduction to what's on the table. In the second part, my colleague Radek will show how some hands-on stuff and show how we feel the simulations are done. Simulations of pump are done in TCAE in our software. And in the last part, there will be a Q&A session dedicated to your questions and our answers. So feel free to ask your questions. We'll be happy to answer them. I would recommend to ask the questions all the time during the webinar. It's easier for us and for everyone. And so don't hesitate to ask your questions. It's your time. Use it to the fullest, and we're happy to answer. So what else? So centrifugal pump. I think we can start. Maybe I should say yes. Together with me is Radek. So let's say hello, Radek. Can you hear us? Can you see us?
Yes, hello, Luboš, and hello to the audience. Yeah, I'm still here. I can still see you, hear you. I think we are ready to move on for the webinar.
It's perfect. So let's get to the action. So I'll start with the general introduction. So yeah, there are a couple of webinars still this year to come. We are having webinars twice a month, I would say. So still this month or on 1st October, there will be a webinar dedicated to external aerodynamics. Later on, there will be a webinar dedicated to centrifugal compressors and Francis turbine, and one for the airfoil acoustics and their potential optimization. And there will be a webinar about wind turbine, and we will finish the season with blood pump modeling webinar in December. Yeah, and also I got the idea. Maybe Radek, we can switch the cameras off, right? Because
okay.
Yeah. I'm pretty sure that still our content is a bit more interesting for the audience than our faces. But we can come back later anyway. So yeah, I think the screen is now bigger, and that's what we wanted. So yeah, so there are a lot of webinars. Maybe we will add a few more webinars with new versions and new developments. So definitely stay tuned and feel free to send us your ideas what else we could do, because we are always interested in your plans and your what you're interested in. Okay, so I'll quickly do the necessities. So I have to say that CFD Support is the name of our company. We are located in Prague, Czech Republic, 15 years in the market, hundreds of consultancy projects done, and based on all our experience and skills and everything, we have created a software which is called TCAE. We have put in it all our energy, all our passion, all our experience, skills, and time, and spend enormous time and effort to deliver this TCAE software, which is I will describe it a little bit more later in the next slides. But it's based on open source. It's extremely flexible. It's extremely usable. It has a huge value cost ratio. It's a really great thing, and we are excited to show it to you and to use it and talk about it and play with it. So I'll go ahead with the TCAE. It consists of several software modules. So there's module for meshing, there's module for CFD, there's module for FEA, there's module for acoustics, there's module for optimization, and other modules are coming. And yeah, TCAE is extremely flexible. You can play a puzzle with it, right? So you can combine it with existing workflow. You can combine it with in-house codes. You can combine it with existing commercial codes or other open source pieces. So there is basically infinite possibilities, not an infinite number of possibilities how to use TCAE, either to start from scratch, to completely start with simulations, or just employ it into existing simulation workflow. It's definitely extremely flexible and usable. That's one important information. Another important feature is it's completely unlimited. So there are no limitations on number of its users, jobs, cores, hardware installations, sessions. So it's completely unlimited, and it ensures that the users can use their resources to the fullest. It's extremely important because then it's effective. There's wide range of licensing options, of course, but the usability is huge. TCAE is focused, and that means it can be accurate. Here's the trick. Software, general purpose software is for everything, and it can be accurate because it has to be robust, and then it loses accuracy. On the other hand, our software is focused on specific simulations, so we never say it's a software for everything. It's software for specific applications like turbomachinery applications and external aerodynamics, and it's particularly really good in these simulations. You can find a lot of examples on our website, so we can talk about it a little bit later, or you can take a look yourself. There's a lot of information, a lot of downloadable stuff. You can download it. There are case studies, there are real cases, including the settings, including the results, including the benchmarks and reference data, so you can make sure yourself how it works, and based on your opinion, you can ask for more information. So definitely, it's focused software. It's perfectly automated, so it can be used as a complete high-end software where all the options are open, or you can use it as a complete black box. Depends on your application and on your projects. There are quite a lot of benchmarks we did in the past. We compared the simulation results with the physical measurements, with the analytic solutions, with all the data possible, and these benchmarks are public, and you can take a look at them yourself. TCAE is also perfectly usable for remote computing. It can be used on the desktop or on cluster cloud laptop. You can use it from home. You can use it in Linux or in Windows. So there are a lot of options and wide range of usability. TCAE is based on open source. This is really important, that I would like to say that TCAE is a mix. It's a package of many open source projects. There are more than 60 open source projects in TCAE, because here at CFD Support we have mastered the process of acquiring open source everywhere available and make it available for professional usage in the industry. So you can imagine that how much time has been spent on these open sources. And on top of them, we here at CFD Support have spent more than 40 many years of development in a team to make it usable in the industry. So the value is huge. We release new versions twice a year. Currently 24.3 is the actual version. And we definitely for the future have a couple of, I would say, cornerstones. We are focusing on the optimization, so that the optimization module is there, it's working, and for the future we will definitely keep developing it because we believe the optimization is the paradigm shift. It's a really big thing going on. So the optimization is one important thing. The other one is the acoustics. So we are very intensively develop the acoustic features of TCAE and the acoustic module, and we have new benchmarks. We have a roadmap, what to do, how to do, and it's a really big thing. So the acoustics, and the third thing is the new simulation module called T-Base, which is being currently developed, and it will allow TCAE users to store the data, to store everything, and create large databases of results, and based on the results, creating his or her own surrogate models, which can predict the results of the simulation very quickly, basically in seconds. But this is the future, and we believe it's really a big thing. Okay. Actually, this is it. So this is the quick introduction from me. Wasn't that quick, but still, it's over. And now I would like to hand over the presentation to Radek. Radek will show the centrifugal pump workflow, how we use it, what's our approach to it, what's the philosophy behind it, and then we will come back. So Radek, the stage is yours.
Oh, thank you, Lubo. Thank you for the introduction. Today's it was pretty quick, so I can directly dive into the practical part of today's webinar, and more or less I will be speaking about the main important part of the workflow preparation. So basically I will be talking what is the input, how the input is imported into the TCAE, and I will say some basic principles about the meshing, about the CFD simulation, and then we can have some discussion about, let's say, about the additional applications like the FEA analysis and maybe the optimization module. So first of all, what you need to have is the input data, which is typically is the input geometry in a proper format. So typically you can use some of your CAD data of your turbomachinery design, somehow process it in your CAD-like software, export it in the STL format, import these STLs into the T-mesh module, prepare the mesh, etc. So, for example, if I take as an example, so what do you need to have at the beginning are the set of STLs which fully describes your flow domain. It needs to have several properties which we have already talked about it. So it needs to cover the basic patch or patches categories, like you need to have the inlet patch, outlet patch, you need to divide the walls of the rotating parts and non-rotating parts. So basically it needs to have some kind of the intuitive splitting of the boundaries of your flow domain to be able to properly describe boundary conditions, interface conditions like on the neighboring components, rotating and non-rotating parts, etc. So basically, at the beginning, you need to have a set of STLs. For example, if I open some of it to show you. So for example, this kind of topology for this centrifugal pump looks like this. So for example, we have first component which builds the inlet piping system or some kind of short extension of the inlet. Typically CFD likes wide enough or long enough extensions to allow the flow to be as steady as possible, and you don't want to have some wide flow at the inlet or at the outlets. So this is the kind of small extension from the impeller part. Then we have the component 2, which is created by the rotating part itself, so by the rotor, shroud and hub. So this example is without the leakages, so it's simplified model without the leakages. So we have just the flow part of the rotor itself, and then directly from the rotor we have the volute component or spiral part, which builds the rest of the domain. And in this way, all these STLs then will be used to define our flow domain. So you need to have a nice waterproofed or watertight geometry which describes your flow domain and includes all the important part which you want to have in your CFD analysis. All right, so this is the some short notice about the input geometry. Then if I directly jump into the TCAE GUI, it is the GUI is split into several parts. First one is the pipeline browser. So these items are used to set up all the modules, to set up the outputs of the simulation, to play with the visualizations, etc. Then you have these properties and other menus. So the property menu includes the setting parameters of each module, and the display and other windows here I used to somehow visualize and play with the properties of the visualizations, etc. So the main part is the properties section. So each module, for example, here in this example, we have play with the T-mesh, or T-mesh is preset, and the CFD simulation is preset, which is the most important part when you would like to go to the FEA analysis with FSI approach, which means you need to have a nice CFD simulation part ready. So first you typically play with the meshing, then you play with the CFD simulation to get a robust outputs and accurate output. Then you need to go for the FEA, and for example at the end, if you would like to optimize your geometry, then if you are very confident with your CFD result, then you can go to the optimization. It's not a good idea to directly, okay, I will do the optimization as soon as possible. I preset the simulation and the meshing very quickly, and I will go for optimization, and I will have amazing results. So it doesn't works like this. So first of all, playing with the meshing. So in this render view, we are stick for a while with the T-mesh module. So here, if you go step by step, so typically each module works like, or each menu which is connected to the given module works like a wizard. So you can go from the top to the bottom overall parameters, and you will not miss any part of the workflow to be set. So let's start with the general section. So here the mesh output is for setting the output of the meshing. So if I would like to simulate just a CFD simulation, I will go for a CFD mesh. If I would like to have some standalone FEA analysis, for example, for the structure analysis or some frequency analysis, eigenmodes, etc., without the CFD interaction or without the FSI. So I can go just for FEA mesh, and if I would like to go for both of them, so I can preset CFD and FEA mesh parts directly in the T-mesh module. But so here we have just the CFD simulation part, because we are importing the STLs, and the STLs can be in several units, typically in millimeters or meters or in inches. So we need to tell the solver in which units the imported geometry is. So here we have, so it means that the scale factor is 0.001 meters, which means that the input geometry is in millimeters. You can easily check if you denote the CFD geometry, which shows you the imported data. And if you go for the information and click, for example, on the dimensions of the, for example, whole component 2, then here you have the information about the bounds, so mean maximum sizing in each direction. And for example, the X direction has 591 of some units, so it obviously it's not meters. So here you can check in which units the input geometry is if you are not sure. All right, so therefore we have the scale factor scripting. Any module, T-mesh, TCFD, TFEA, or even TOpt has its own scripting interface. So here you can import Python script with some interface to the parameters of TCAE, and you can adjust the workflow to your needs. So you can really tailor the workflow with the specific features, with the specific functions or operations. So even if you find some functionality which is not available directly in the GUI, it can be somehow implemented or imported via this scripting feature for all modules. Then we jump into the CFD section. Here we have rotation reference frames. So for rotating machines, we need to have at least 2 reference frames. One is static, the second one is rotating. If we have just one rotor, so typically the axis of rotation, which is defined by the direction and the origin, should be the same. And just by assigning static or rotating, you are distinguishing if the given part of the geometry will be rotating or not. So we have 2 reference frames. Then in the component, the main work has to be done. So basically here you import the geometries, or even what I haven't mentioned, that you can also import the ready to simulate volumetric mesh, ready for CFD simulation. It can be imported in 3 different formats. First one is the OpenFOAM mesh. Fluent MSH mesh can be also imported, or a more general format, the CGNS mesh can be also imported. You can also combine. So for example, component 1 can be imported or generated by importing the STLs and generating the mesh within the T-mesh module. But the second component, for example, can be an imported volumetric mesh, which is ready by your own code or different meshing tool. So this can be combined. In case of external mesh, you just need to play with the patches in the table, so it will be automatically loaded, and you just assign the proper types, like what is the inlet, outlet, what are the interfaces between components. But if for case of the importing STLs, you need to set all the meshing parameters. So again, you just set the types, you just set the reference frame. So typically, for example, for the rotor part, each part can be rotating. You can combine that even in the rotating region, which is defined here, the reference frame. It means that the whole component is rotating. You can define the static part in the rotating region or rotating part in the static region if this rotating part, which is then assigned some rotational velocity wall on the rotating part inside a stationary component. So this part has to have the rotational symmetry, otherwise it needs to be included into the rotating component. Then we have this minimum refinement levels. So for those who are familiar with SnappyX mesh, which works with some kind of initial background mesh, and then it starts splitting the cells with the rules or with respect to the refinement level. So if the cell is intersected by some part of the geometry, then this cell will be splitted up to the given level. You can set some kind of range, minimum, maximum level. Then these numbers are led by the local curvature. So if the surface is curved, highly curved, then the maximum level is applied. If not, if it's flat, then the minimum level of refinement is applied. There are many options how to locally refine the mesh. So first one is the patch-based refinement, let's say. So for each patch, you can assign different level of refinement. Therefore, it is clever to export more parts for the rotor, for example, than just one, because then you have more complexity, more free space to play with the local refinement. Another option is to use, for example, these refinement regions. So you can define a region within your, in this way, for example, within your components, and all the cells which lies in these simple shapes will be splitted up to the given level. So it's not applicable here, but for some other application it can be handy. One important notice that for every component you need to put the internal point inside the region where you would like to create a mesh, which is done by this by this internal point, which can be visualized by checking this show internal point sphere with radius option. And if you like to see inside, then you can click on the CFD geometry, go to the display and decrease the opacity to see where the point is placed. So be sure that it is somewhere in the flow domain for for each component. Then what we have here is the component map. So here you see how the components are connected. The connection is done by adjusting the particle type of the boundaries, and to connect two components, typically the outlet interface is connected to neighboring inlet interface, and it is done by right-clicking and connecting to a proper part of proper component. So in this way, at the end, you should see nice topological graph from the inlet to the outlet. Then for some kind of advanced playing with the mesh, there are all the parameters of the SnappyX mesh included here, so you can play with it as you need. Typically for users who are not so experienced with the Snappy, you just need few of them. Typically you need a layer mesh part. So if you would like to add the boundary layer for better accuracy and better capturing the flow at the walls, you can add the boundary layers. So if you would like to add boundary layer on the, for example, impel part on the hub, so you just put here a number. So this number means how many inflation layer will be added. And then the particle parameter of the inflation layers can be set here in the layer mesh section. So here is the standard, let's say, parameters of defining inflation layer, like the expansion ratio, thickness of, and you have three options: final layer, first layer, or whole boundary layer thickness. You can switch between relative sizes, which is more general. So these values are connected to relative sizing for the given part of the geometry relative to the size of the cell, resulting cell size at the given wall. If you go to the absolute, then it means that these numbers are in millimeters or meters, depending on the units of the input geometry. So we typically use this relative sizing for complex geometries. The other one are additional parameters of meshing. So typically you don't need to touch them because they are set to some kind of default robust values. And the last parameter is the number of processors. So the mesh generation can run in parallel, and you can use as many physical cores you have. So my computer has 10 cores, 10 physical cores, so I can use all of them to, to speed up the mesh generation process. Right, when everything is preset, you can go for the meshing. So maybe I've run this simulation before the webinar, so maybe I can then switch to some template and show you how it works. Maybe I can do it right now. Let me open the project without any computed values. So I am opening the project directly. So you can go to your file browser, and typically by right-clicking, and you can click open in TCAE, and the project is directly loaded into the GUI. So this is this one, right? So yeah, it is okay. So yeah, because I have several versions here, I have here the brand new test version of the latest TCA release, the developed version. So therefore, it asks me that I am opening the project in the previous version. So if I would like to transfer it into the newest version, so this was not my intention, but but as you can see, the GUI looks the same like the previous version. And just to show you how to generate the mesh, sorry, we can go to the manager, which is typically the first item here in the pipeline browser, and we can click every component manually, or we can click mesh all for meshing all the parts. Okay, so because I'm in the beta version, there's some kind of problem. Let me click on check. Or oh yeah, I think there is a problem because I'm using all the physical cores here, so it doesn't allow me to run additional simulation. So we need to wait. But by clicking, I've shown you, by clicking manually on these buttons, it will run the mesh generation process, and whenever it is done, the buttons appear or changes to green, and then you can click show these parts. The CFD mesh is hidden under the CFD mesh item, so you can visualize it or hide. And whenever the mesh is visualized, as I did here, you can play with the visualization. So you can here click surface with edges to see the topology, and or you can visualize just in this multi-block inspector. You can just visualize any patch of the loaded parts. So in this way, you can play and you can check if your mesh looks like you expected, if there are no distorted parts, and if everything is smooth and nice. So in this way, you can visually check all the parts of the resulting mesh. So for example, here I have just blades, parts, etc. So in this way, you can visualize the mesh. All right, whenever the mesh is ready, you can go for the CFD simulation. So CFD module consists again of several menus using which you preset the whole workflow. So let me be quick of introducing the TCFD module. I think several parameters are really similar to any other CFD code. So if we go quickly through of them, or maybe I will go back to the non-running, because when I am in the running project, so now the simulation is running, I'm not allowed to change the parameter that can't be, sorry, TCFD that can't be changed during the simulation. There are some, for example, some kind of numerical like parameters using which you can for example change the relaxation factors and some kind of numerical parameters for the bounding tools or whatever. So these can be changed during the runtime, but those who are hidden or freezed, as you've seen, like the boundary conditions, then they can't be changed during the simulation. So let me go back to non-running project, to TCFD, and go step by step. So in general, simulation type, because we are focusing on turbomachinery, and each turbomachinery family of machines has its own efficiency formulas, etc. Some specific parameters. So this workflow is split into the particular applications like pumps, hydro turbines, wind turbines, compressor, etc. So you need to choose your actual simulation type. So we have pump. So then we have simulation type pump. In the physics, here you set some kind of time management. Here you can run or set steady state or transient simulation, or both of them. Fluid properties, standard, you choose the physical model. Because we are in the pumps, so we have just the incompressible model for water with the standard parameters of the fluid, like the reference density, dynamic viscosity, etc. Rotational reference frames, here you set which rotational reference frame is rotating. So typically standard, the static is static and rotating is rotating with a particular rotation speed in the given units. You can either choose radian per second or RPMs, revolutions per minute. It follows the right-hand rule. So therefore, if you would like to change the direction, you need to change the sign of the value of the speed of the rotation. Multiphysics, here you can enable some additional multiphysics to be enabled, like the cavitation risk. Here you simply set on which patches you would like to compute the cavitation risk. You just follow or measure or monitor the pressure at the walls, and if this pressure is below the saturated vapor pressure, then it somehow denotes or it computes some statistics at the end, and you can have some guess about the cavitation. Even this simple incompressible model doesn't include any physics of modeling the cavitation. So you can enable it here. There are some additional tools or multiphysics to be applied, like passive scalars, porosity zones, etc. In the turbulence model, you can choose your favorite turbulence model, which is connected to your application. Inside the simulation, here you can play with the solver setup, like number of processors. Again, in Linux, I'm in Windows. In Linux machines, you can also set the host, so you can easily run it on several nodes connected in the cluster. Here in the runtime evaluated quantities, you can ask for some specific quantities to be evaluated above the standard values, standard quantities like pressure, velocity, turbulence quantities, etc. So you can ask for it. Here, efficiency probe, as I mentioned, every rotational machine has its own efficiency formulas, which are evaluated typically by the difference of pressures at the inlet and the outlet. It includes the torque to compute the power, and so on. So here we have three options for efficiency probe to be set. First one is choose to first item to choose is the inlet patch or inlet patches, which are used to evaluate the pressure or velocities at the inlet or at the interface you want. So for typically, if you would like to see just the efficiency on the rotor itself without the volute or without the suction pipe, then you can switch to the given interface. The same holds for the outlet patches and torque patches. You just list all the rotating parts which you would like to include in the evaluation of the torque. You can also add the forces probe. So if you like to evaluate the forces on a particular patch, on a particular part of the geometry, you can do it here. You just choose on which patch you would like to evaluate the forces, and there are some standard quantities which are evaluated, like force in all XYZ direction, moments in all directions, and a given point. And for example, for external aerodynamics, you can also put the parameters to evaluate drag and lift and moment coefficients if you need. Probes. Here you can put a virtual point into your flow domain to evaluate the particle fields in the particle point within your simulation domain. Convergence check, because we are in the stationary application or stationary solver, so typically you need to have a converged quantities at the end, and typically in advance you don't know when the solver converged, so you can set the criteria to stop the simulation before the maximum iterations are reached. So we can set the quantity. For example, I would like to stop the simulation when the efficiency, the average efficiency, is less than 0.5% or 0.05% in the absolute manner, or it can be set also relative to the actual values of the solver. And you can choose any quantity which is evaluated, and there are many of them. For example, head, flow rate, total pressure difference, etc. Here controls, I have already showed this part of the menus here. So here you can set the relaxation factors, some kind of boundings for the pressure and velocities, and some kind of equation solver connected parameters like the absolute tolerances or relative tolerances for the iterative processes. Again, here you can put your script or enable scripting options to tailor the workflow to your particular needs, which are not implicitly implemented inside the GUI or inside the whole workflow. So by this, you can play with the workflow itself. Boundary conditions, I think it's clear. So you need to define inlet and outlet boundary conditions. Here, within this workflow, you can simulate the whole efficiency map within a single simulation. So you set more points, and for each point you set different boundary conditions, for example, volumetric flow rate, and then at the end you will see the result for all the points in which are tabulated or graphically depicted in the nice graphs. The same boundary conditions has to be also applied for the walls, for the interfaces, and last but not least, you need to set some kind of initial condition, initial guess for each, for the pressure, velocity, and turbulent quantities, which can be done here. And last, for the just to see results and some kind of report, here you can set some specific post-processing tools like Turbomachinery connected visualization, like blade-to-blade views or meridional averages. Here you can adjust the reports. I will show you in a while. So the report, HTML report, is automatically generated and includes all all the parts which you ask for, like efficiency, torque, head, power. So if you are not interested in some of them, you can uncheck them here. You can choose your favorite units, and you can include some additional data files. For example, if you would like to compare with previous simulation or with the measurement data, you can import a CSV file with the data of, for example, efficiency versus volumetric flow rate, and this can be then imported into the graphs inside the report. There are some additional tools, like you can export data on any wall for some additional post-processing or external tools, and the same can be done for saving all the data in CGNS format, or just writing the surface quantities with the forces, for example, some external FEA analysis or any other analysis. Okay, and whenever, again, your CFD parameters are set, you can simply hit the Run All button, which runs the whole workflow. It creates the mesh if it's not already created, and then run the CFD simulation. So we can, what is happening during the simulation, we can see here. So you can see here in the TCFD run the statuses. We are simulating 7 points now. The third point is running. 300, almost 350 iterations are already simulated for this point, and some guesses of simulation time is for the current point and for the overall simulation. During the simulation, you can watch. So let me see if I have. Yeah, during the simulation, you can watch the residuals, for example. You can watch the convergence of any quantity. So here we have the efficiency, but you can also add, so you can split the screen as you need. So you can add, for example, a new line chart view here inside the TCFD item, and inside the quantities, you can evaluate any quantity which is evaluated. So here, for example, we can add a head and get rid of the mass flow rate. And when I click into this view and click this rescale or reset view, maybe I can enlarge it. So here we have the iteration process for the head by mouse or by clicking here into the view. I think here some kind of left axis custom range, so you can set the range of the view. So for example here for 20 up to 35 meters, and you can zoom the view by manually or by playing with the mouse. So in this way you can watch any quantity you need. During the simulation, what you can also do is to view the current time step. So it will visualize the result at the given iteration. So some kind of, you can watch the intermediate results. It is handy or useful when the simulation doesn't converge well, something bad is happening, so you can visualize what is happening and where, and maybe you can find some flaw or some bad parts in the mesh, and then you can stop the simulation, redesign the meshing parameter, and rerun the simulation. Some kind of fix bad meshing, for example. Yeah, and now you can see here you have new item of the current iteration running, and you can visualize like for the final simulation. Whenever you visualize that data, there are also the previous results. So depending on how many iteration is done and how many points you have, then you can go through the already simulated points to check them visually, to play with the visualization or whatever. So this is the visualization. Maybe we can show some specific visualization techniques at the end. And during the simulation, you can also ask to generate a CFD report. Typically, you can ask for the light CFD report, which generates just kind of, yes, I played with a lot of parameters, so I need to save the current setup. And now I can click the light CFD report. So I hope, yeah, so now the light report is generating, and we will see it in this HTML view window whenever it's generated, and we can check again, not visually, but some statistics about the currently running simulation. And of course, at the end, you will have the full report with all the sections and all the parameters evaluated for the final results. Right, so let's wait for it. If you have the results visualized, either the intermediate results or the final one, you typically see such an item here, which include all the parts of the geometry. So the internal mesh is the whole volumetric mesh, or you can visualize just just the part of the patches. For example, just the impeller. You can see all the quantities you asked for evaluation, like wall shear stress, cavitation. So maybe there are some parts where cavitation can occur, for example here on the leading edges, but this is the intermediate results, I guess. So if we go further, okay, so maybe for this one, you will see additional results, which is connected to the given boundary condition which you preset. So in this way, you can visualize and do nice visualization and analysis of your results. Maybe. So this was about the CFD, and this HTML report is generated. So you typically see the simulation statistics of the currently run iterations. So you see the convergence of, for example, flow rate, residuals, and the basic quantities like the head, efficiency, etc. So basically at the end you will see the whole table filled with values and the graph for all your points. So this is the HTML view. And if you have the data and workflow tailored to do the FEA analysis, you can then anytime enable the TFEA module. So let me maybe borrow some of additional example. So you can see that you will see that just you enable the TFE module, you prepare the mesh for the solid of the impeller. So the simulation or the setup is for the CFD part and meshing part is the same. In the T-mesh part, you just add the meshing of the FEA solid. So let me show you. So this is the example of the pump, which includes the leakage because you would like to include the whole solid of the impeller into your flow domain. So if I get rid of the CFD geometry, here we have the FEA geometry imported. So this is the solid. In the T-mesh, you have here FEA part. So here in the similar way, you import your surface geometry of the solid. You adjust just few parameters, which is typically maximum and minimal sizing of the tetrahedra of the resulting tetrahedral mesh, which is used for the FEA analysis. And basically that's all. And then you go for the TFEA module and you set again some kind of finite element analysis parameters. So here you can enable the fluid structure interaction with TCFD results. So the results are automatically taken from the given patches. So for example, here just for blades and the fillets, you ask to map forces. If the simulation includes also the temperature, you can map the temperatures. You can ask for the model analysis to evaluate the eigenfrequencies of your solid at the given CFD conditions, and some additional parameters like the solver setup, again the scripting, important material properties like the steel. You can also newly include several materials, so the solid can be composed of several parts, several different materials. Then you set the boundary condition, which is typically here the zero displacement region, so some part of the solid is fixed. You can set temperature regions if there are some, if your object improves to some external temperature field or whatever. And you can also add some kind of loading regions. So you can explicitly say which forces are acting and where. And again, the post-processing, so you can adjust the report, and at the end you will see the FEA report like for the CFD simulation. And then you also will have this kind of evaluation of von Mises stresses, visualization of von Mises stresses and displacements. And also the results can be loaded in the graphical user interface. And the last application can be the optimization. So if you have some parametric model, so you can connect it, the model, the parametric model. So typically, if your geometry is parameterized, and you can ask, okay, this for values of the several parameters, and the tool will give you the new set of geometries. Then it can be also connected with TCAE in the same way. So the TOP takes care of connecting the external tools, typically the geometry generators, with the TCAE, and then you can preset for some kind of parameter like number of blades or curvatures of the of the impeller blades or whatever. Any parameter can be chosen, and then you can run DOE or optimization with respect to the, for example, efficiency or whatever you would like to optimize. And then at the end, I think this is a simple example of DOE for different number of blades. So then at the end, you will have the set of simulations with respect to all the simulated combination of the parameters. And I think you will also have the TOP report, which includes all the results for all parameters from the parametric space, and you can watch how power efficiency or whatever changes with respect to your combination of the parameters. So maybe I was long enough. So I think it's time to go back to Luboš to give you some last information and conclude the webinar. So I think I'm done at this point with my presentation.
Thank you, Radek. It was great. I liked it very much. Thank you for your part. It was very detailed. So we are moving a little bit in the webinar. So I would like to ask the audience to ask your questions. So there's a menu in your client. You can ask your questions there, and we will be happy to answer them. So feel free to ask your questions. Use your time to the fullest, and we'll be happy to answer. We are waiting for your questions. We will do our best. In the meantime, I would like to point out my hard message, which is that the technology is only about 40% of success. The rest is your skills, experience, patience, and dedication. Because it's the effort what makes great results, and technology is still just a set of tools, but the way how we use the tools makes the difference. So it's very important. Whatever you use, you still have to. You should be a good engineer. It's much more about engineering than about the tools. That's my message. I hope it's understandable, and let's definitely move now to the Q&A. So okay, so questions. Here's one. So Sergio is asking whether TCAE can simulate the ideal RPM, or if the RPM can be a result of the simulation. Radek, would you like to answer this one, or?
Yes, I can. Maybe can I share my screen again? For example,
of course. I can do it. Yes.
Okay, so I can go to the TOP module if I have still open it. Okay, so generally it is possible because you can combine any parameters in the TOP. So you can also go for the parameter keyword. You can ask for the RPMs, for example, and you can vary RPMs. So if I found it, so somewhere here it will be, so angular velocity, or what is that? So you can, I mean, I don't see it, but somewhere it should be there. Reference frame, angular velocity. So you can vary the angular velocity as the optimization parameters, and your tracked quantity. If I go to the optimize module, you can set your optimization function that will be some kind of difference between the torque and your target torque, and you will minimize this value with respect to the RPMs. So yes, this kind of simulation can be set. Yeah, so you can ask for the built-in quantity, which is, it could be efficiency, but it can be also torque. And then optimization can be, I don't know, 5,000 Newton meter minus the torque. And this will be your optimization function in absolute manner, of course. So something like this. And this will be the optimization function, and the optimization tool will go to find a parameter to reach the torque of 5,000 Newton meters, for example, and go for minimum. So this could be one of kind of optimization, not geometrical, but to target some parameter, to optimize some parameter itself.
Thank you, Radek. It was really good answer. Thank you.
Welcome.
The next question is, Ahmed is asking what turbulence models are used for the pump, or would you recommend one?
Okay, so in general we use the K omega SST. So, but in general, if I go for the physics turbulence, so K omega SST is a standard, but sometimes we also see that you can go for a realizable K epsilon, but it always is connected to the given application and to the experiences with the model. But we, in 95% of cases, we typically stick with K omega SST model. But it depends on the user and on the application, of course.
Okay. Yeah. So yeah. This is it. Nicholas is asking about the possibility of external mesh, but I think it was mentioned during your contribution, Radek, right?
Yes. I mentioned, maybe I was too quick, but yeah, you can import. Let me show you. If I go back to one of our example, T-mesh components, and here you can import volumetric mesh in a given format. You will locate on your disk. It will be automatically loaded and can be used for the simulation directly. And as I said, you can also combine, different volumetric meshes with the STL import, for example, of another component.
Yeah, I would also comment on this, that our typical first choice is SnappyHex mesh, because we have a lot of experience with it, and we have made really a lot of successful projects with it. So our if we do the project here as a consultancy business, our first choice is always SnappyHex mesh, but yeah, we never push too much pressure on what mesh should be used. So it's definitely, the external mesh can be created in external software and loaded in TCAE. It's not a problem. A lot of users do it and they're happy with it. Okay, so it's the mesh. Also, we have one question about the interface. Right? Can you comment quickly the interface between the impeller and the volute? Just two quick points.
Okay. So let me. I think I can visualize it here. Go T-mesh, CFD geometry. Okay. Yeah, great. So the interface we call the common part between two neighboring components, right? So for example, if I go to the inlet section, here I have the outlet interface, so the inner part of the suction suction component, and the connected part is the inlet component into the rotor. And these two interfaces, because the components are meshed separately, so we have two patches, and these patches has to be connected, which is done by right-clicking, setting to which patch will be connected, and then on these interfaces you can set the boundary conditions, so the way of communicate the information at these interfaces. So here in TCFD section, interface conditions, here you can set either the AMI approach, which is a direct mapping, yeah, so the interpolation between these two sides, or you can go for mixing planes, but here I can choose it because my simulation is running. And mixing plane is typically applied for the segment-like geometries, right? When you have just one segment of the blade, it has to be connected to the part which doesn't fit perfectly. So typical application is a section of the impeller connected to the full volute geometry. So then you can apply the mixing plane approach. So
Okay. It's this one. Also, question from Jürgen. Would it be possible to use cylindrical background mesh for the impeller, and the Cartesian mesh for volute, for example?
Yes, it is. So, for example, here in this case, we have the background mesh or hexahedral background mesh for all the parts. Yes. But if the situation is handy to apply the cylindrical background mesh, you can do it. So if you enable the cylindrical background mesh and you adjust the parameters to follow the topology. So for example, typically for axial fans, it is a good solution. It can be a good solution, but sometimes because the shape of the cylindrical background mesh are too different to the hexahedral shapes. So then sometimes with the snapping to the weird or to complex shapes can be not good. So it depends on the scenario, but the answer is yes, you can combine it. So you can, for any component, you can set either hexahedral background mesh or cylindrical background mesh, and you can play with the parameters. And for some scenarios, it can generate nicer and more effective mesh compared to the standard hexahedral mesh. So I hope.
Yes, it's a good one. It would need maybe a bit more detailed discussion, because as far as I know, we have this option, but we don't use it very often, right? Honestly, what was the reason why we are not using it?
Because, for example, for these impellers or radial centrifugal fans, the tricky part that still the mesh is not fully symmetrical, because it has this topological shape, right? Inside there is the hexahedra, and then
the core inside.
So the core is not symmetrical. Yeah. So therefore, I think we applied for some axial fans with large hub diameter, where you really have the hole, basically the large hub, and you can really apply this symmetrical part of the cylindrical mesh. And for such a scenarios, it can be useful, and it can save some count of cells. It can properly fit the hub and shroud contours. But in general, we haven't used it so often, only rarely.
Quite rarely, and it's the reason is these like the center of the rotating part, right? The impeller.
Yes.
It never proved to be too much valuable, but it's possible, and it would need more discussion for particular case, if it's suitable for the case or not.
Yeah, right. But you can in general you can play with the parameters. For example, you can change this radiuses. So let me try something, if I remember it correctly or not.
There are certainly some parameters which you can play with and make them make the core like very small or big, or also the curvatures and the gradings can be they can be definitely.
Yes. But the topology changes drastically. You can do it in this way, but then you have really thin, not nice cells in this area.
Right.
So if you enlarge it, then this unsymmetrical part can go into your symmetrical part.
In general, I would say this like cylindrical background mesh is intuitively looks good because it's aligned with the rotating speed, right? It's quite aligned with the rotation. So intuitively it should be good, but it definitely deserves to be tested more. And yeah. Let's finish here because we don't really have any conclusions here. So
so it's very specific to the application.
Okay. Yining Ken is asking, is it possible to simulate the balance holes in the impeller, and is it possible to simulate the radial and axial forces? So you can definitely simulate forces. You can. There are tools for it.
There are also we evaluate automatically. The radial axial forces are evaluated, and if you have the geometry which includes the holes in the impeller, then it can be included in the solid. And the answer is simply yes. And we have customer who already who simulated and are simulating these days.
And if I read between the lines, it's the case with with the back of the impeller, and
yes, exactly,
also the issue with the pressures. So yes, it's TCAE is ready for that. This is a little bit difficult to explain because yes, you can have the impeller in space and it can have holes. For accurate results, we would recommend, I guess, transient simulation, right? Because
could be, but I think maybe with the even with the stationary one, you can have a good guess, because there are some holes in the rotating region, so it can be simulated. It's more complex geometry, but if you provide, for example, in this case, if your CFD, if your patches of the impeller has the holes, include the holes, then the workflow remains the same. Like
the workflow is the same, and you have to have the whole impeller, right? Also including the backside and everything, have it in fluid.
As I am showing right now, so this is the case where also the leakage is included. So the whole solid of the impeller is included into the simulation, like the wetted part. And if there are holes which goes from the front part, from the hub to the shroud, then it's there, and the workflow remains the same. So it can be done.
Okay. So this also answers the question whether it's close to reality. The results, yes. In general, these turbomachinery applications are very accurate. You practically can't imagine better results. Of course, close to the best efficiency point. The more far you're from the best efficiency point, then the results could differ from the measurement, for example. But standard cases are very accurate. You can they're nearly perfect. Okay, I think unfortunately this will be it, because we have run out of our questions and also of our time. So I guess we will conclude here. So I would like to thank everyone for your attention and for your time. And let us know if we can help in the future. It's our job and a pleasure. So let us know, and we will definitely talk to you and discuss and see what we can do together. So maybe, Radek?
Yeah, I think that's it. Thank you for watching, and we are looking forward to your further questions or to see you on our next webinars. So thank you and enjoy the day.
Okay, thank you all. We leave you with that, and bye-bye for now. Thank you. Bye-bye.
Bye-bye.